Welcome back. My name is Clayton, and I'm just going to be covering the practice problems from your resonance quiz. So question number 1 here. How many resonance forms does the following compound have, including the one shown? And we're not going to talk about the expanded octet of sulfur in this question. So here we have our compound. And when you're talking about resonance in a general chemistry class, typically what you're referring to is the arbitrary decision that we made here to put the double bond between the left oxygen rather than between the top one or the one on the right, right? I mean, there's no difference between those oxygens. I could have chosen any of them. When we see that, oh, right, that's resonance, right? So if I were to have chosen those other oxygens instead, I would get this for one of them. Fill in all these lone pairs, and I would get this option. So that last one filled in the top, and this next one will put the double bond on the right oxygen. And that is the whole thing. So how many do we have? We have a total of 3. All right, which bond is stronger in this structure? So let me rewrite those. Okay, so this is a little bit of a trick question because the goal here is to recognize that this is a resonance, just one of 2 resonance forms here. And so in reality, neither of these resonance forms is what this compound, sulfur dioxide, actually looks like in real life. It's, it just shows where the electrons could be, but in reality, it is kind of a combination of both of these. So if I were to draw something like this and that's closer to what it looks like in real life. And so really, is that a double bond and is that a single bond? No, that's not true. They're both kind of somewhere in between a little bit. And they're also equivalent to each other, right? There's no difference between these 2 bonds at the end of the day. And so these bonds are equal. Which mechanism reflects the movement of electrons within the compound below to show the resonance form on the right? So I'm not going to worry about drawing the whole thing here. I'm going to put carbon with the 4 bonds that it has. Oxygen has a lone pair. And we'll put our carbon here, what it looks like on the other side. And we're just going to compare the differences now. So on the left, we have a pi bond, where on the right, it is gone. On the left, there is no extra lone pair up here, but it's right here. So really, if we just evaluate the left and the right, I can see, oh, this lone pair is brand new, and we lost something here. So these electrons must have gone into, localized onto the oxygen. That's what we're talking about here, right? And so our mechanism arrows look like this. Boom, just one arrow from the bond to localized on that oxygen. Remember, arrows always have to start where electrons exist. So a bond, they can start at a bond, they can start a lone pair. But if you have a deficiency of electrons, they will not start there. All right, that pretty much does it. Again, my name's Clayton. We will see you in the next one.